Hello, good afternoon everyone. Welcome to my course Physics 1. This course is generally made for undergraduate level BTech degree students. Myself, Gopal Chakraborty, Assistant Professor, Department of Physics, Greater Kolkata College of Engineering and Management, Badaipur. You can personally meet me at college premises, ground floor physics lab. You can also send me a mail regarding your query and doubt to the given mail address, that is godphysics6@gmail.com or gopal.chakraborty_gkcem@gisgroup.org. I have a YouTube channel. The link is given here. So you can subscribe my YouTube channel for more similar videos. So the students, you can attend that video lectures that I have uploaded for the subject Physics 1 as per Macau syllabus curriculum. And if you find any doubt, any query, please feel free to contact me at my given mail address or directly at college. So I am the subject teacher for today's course. The corresponding course pages are www.macoutexam.net and www.macoutwb.ac.in. The syllabus for the subject Physics has already uploaded in the university website, so students, you can easily download the syllabus from their university webpage. The title of the course is Physics 1. The subject code is BSPH101. It is under the category of Basic Science course and it has a credit for 3 lectures per week and 1 tutorial per week. The course is generally made for undergraduate level BTech degree students of first year. So computer science, civil, mechanical, these departmental students will going to study this course in the odd semester, and alternatively electrical and electronics departmental students will going to study this course in their even semester, and the subject code in that case will be BSPH201. The syllabus is almost same for both odd semester and even semester. Now the topic that I will going to cover are one-dimensional time-dependent Schrodinger equation for free particle and three-dimensional time-dependent Schrodinger equation for free particle, one-dimensional time-dependent Schrodinger equation for a particle acted upon by a force field, and three-dimensional time-dependent Schrodinger equation for a particle acted upon a force field. So these topics are also under module 4, that is quantum mechanics. Prerequisites for these topics are elementary idea of quantum mechanics, fundamental idea of mathematical calculations, and also you have to know the idea of quantum mechanical operators. The course objectives are idea about time-dependent Schrodinger equation, both for one-dimensional and three-dimensional cases, and the characteristic of Schrodinger equations and its solution. So after completion of this course, students will able to know the basic idea of one-dimensional and three-dimensional time-dependent Schrodinger equation and its solution for a free particle without presence of any force field. And second one, student will also able to know the basic idea of one-dimensional and three-dimensional time-dependent Schrodinger equation and its solution for a particle acted upon by a force field. So these are considered to be as a course outcome. So students, this is the fourth class of quantum mechanics. So I think if you had missed the previous three class of quantum mechanics, please you all gone through this three class or three video lectures that I have uploaded in my YouTube channel, because before explaining the Schrodinger equation, you need to know the basic idea of quantum mechanics, because without having that idea it will be very difficult for you to understand the Schrodinger equation. Okay, so better you just those who have missed those class, please just check that videos. Okay, so where I have explain the basics of quantum mechanics. Okay, so as the quantum mechanics, I have told you that in quantum mechanics any physical quantity is described by a probabilistic way by considering a number of allowed values with different probabilities. So thus the explanation of nature or physical phenomena in terms of quantum physics necessitates that the transition from deterministic classical physics. Okay, so here you know that the wave function plays an important role, because the how can you define that particle when a particle is moving in some space? So the space-time behavior of that particle in quantum mechanics, which is a moving, that particle can be described by a function. That function is known as wave function. Okay, so here the Schrodinger equation is also associated with that wave function, and you know that the wave function must be single valued, continuous and square integrable. The space derivative of these wave function also must be continuous, single valued. Okay, so these are the conditions required for a wave function. Also these are the basic properties of wave function. And you also need to know what is the idea of probability, because you can define some particle, or the chance of getting the particle is maxima when that particle moving for a particular boundary region, and corresponding probability will be maximum. That means that value will be equals to 1, or in that case when there is a chance of getting the particle is less, so that the probability corresponding to that particle will be minima, that value will be equals to 0. And so these are the things that you need to know. Also you need to know that what is normalization factor, what is normalization condition, because I just try to remind you that in case of a normalized wave function, that means for that particular wave function the probability will be always maximum. So for the condition for normalization factor that will be for which the probability will be equals to 1, that means maximum. So these are the things that you need to know in details for today's class to understand what is Schrodinger equation and corresponding solution. Okay, and now I will discuss you regarding the Schrodinger equation. Now Schrodinger in 1926 considered that if a particle have wave properties, that means matter wave, there should be some sort of wave equation which can describe the space-time behavior of the quantum mechanical particle, as example electron. So therefore Schrodinger equation Schrodinger wave equation describes the behavior of a wave function. Therefore space-time behavior of a moving particle associated with matter waves under the different physical situations. Okay, so this wave equation can be developed both for time dependent and time independent states. So what is time dependent equation? So here the potential energy depends on time. So that the wave equation describes the change of position of the particle with time. And what is the time independent wave equation? For time independent states, that means the potential energy capital V of a particle does not depends on the time explicitly. So potential energy V, or the force, where you know that force can be represented by F equals to minus of grad V, where V is the potential and grad is the vector differential operator. So F equals to minus grad V acting on that particles varies only with the position of the particle, and thus the wave equation that can describe only the position of the particle is called time independent Schrodinger equation. So now I will show you how you will develop, construct that both the time dependent and time independent equation. So here for today's class I will show you only the time dependent wave equation for one dimension and three dimensional case. So now the first case, where the one dimensional time dependent Schrodinger equation for a free particle, how we are going to derive or construct that differential equation. I'll give you first the what is the basic idea. Okay, as you know, the wave function psi can be represented as a e to the power I kx minus omega t, where k is the propagation constant and omega, that value is equals to 2 pi nu. Okay, omega is the angular frequency of oscillation. So the basic concept is that you have to take the first order derivative first with respect to position, then again second order derivative of that wave function psi with respect to position, and that will give you some value of in terms of the kinetic energy E. Again you take the first order derivative of that wave function psi with respect to time t. From there you will get another expression in terms of kinetic energy. Now from these two equations you just try to equate the value of this kinetic energy. From there, equating these two equations, you can easily construct the differential equation for one dimensional case. It is then called the Schrodinger equation for free particles. So I will now show you step by step how we are going to construct that Schrodinger equation. So a subatomic particle, say for an example electron, proton, neutron, these all can be represented by a wave packet formed due to the superposition of number of harmonic waves having varying length lambda. Okay, so a wave packet having a wave number k equals to 2 pi by lambda of angular frequency omega moving along the positive x direction can be represented by psi function of position and time, that's equals to a e to the power I kx minus omega t. So a is the amplitude. Now as we know, according to de Broglie hypothesis, the momentum of that particle having wavelength lambda, that can be written as p equals to h by lambda, where h is the Planck constant. So you can multiply this equation with 2 pi and divide by 2 pi, so that you will get h by 2 pi into 2 pi by lambda. So that is equals to h cut k. H cut is the reduced Planck constant. So your momentum, that equals to h cut k. Now see the look that what will be your kinetic energy of that particle of mass m. Now the kinetic energy E, that's equals to p square by twice m. So p square equals to h cut square k square by twice m. So that can be represented by h cut nu or h cut omega. Okay, so h by 2 pi into 2 pi nu, so that the kinetic energy can be represented as h cut omega. So now so you know the momentum equals to h cut k and the kinetic energy value is h cut omega. So that will be denoted by equation number 8.9 and 8.10. Now as I have already told you that you just take the first order derivative of the wave function psi with respect to position x. So you will get del psi del x, that's equals to I k into a e to the power I kx minus omega t. Now you just taking the second order derivative with respect to position, and so you will get del 2 psi del x square equals to minus a k square e to the power I kx minus omega t, because I square will give you minus 1. So you will get ultimately del 2 psi del x2 equals to minus of k square psi. Okay, so that will be represented by equation number 8.11. Now again that I have told you that secondly you try to take the derivative, first order derivative of wave function psi with respect to time t. So as we know that psi equals to a e to the power I kx minus omega t. So the time derivative gives you del psi del t, that is equals to minus I omega of psi. So now multiplying both sides by minus h cut square by twice m. So if you multiply the second order derivative of psi with respect to x with minus h cut square by twice m, so you will get minus h cut square by twice m del 2 psi del x2 equals to minus h cut square by twice m within bracket minus k square of psi. So minus minus will be cancelled out, ultimately you will get h cut square k square by twice m of psi. So that value is equals to h cut omega of psi. So as we know you can represent equation 8.13, that value equals to E of psi, where is the kinetic energy. Now multiplying both sides of equation 8.12, that means the first order derivative, time derivative of wave function psi by I h cut, that will give you I h cut del psi del t equals to I h cut within bracket minus I omega of psi. So that's equals to again h cut omega of psi, that means E psi. So you know that 8.13 and 8.14, so right hand side is the two equations are same, so you can compare or equate these two equations, and thus you will get minus h cut square by twice m del to psi del x square equals to I h cut del psi del t. So these equation 8.15 represent one-dimensional time-dependent Schrodinger equation for a free particle. Okay, the second case, that is one-dimensional time-dependent Schrodinger equation for a particle acted upon a force field. Okay, so in that case again I explain you how we will going to derive this Schrodinger equation. The process is very same as I have discussed for the first one. So here, as we know, if P is the momentum, so the total energy of that particle, that can be represented as E, that capital E, equals to kinetic energy plus potential energy. So here the kinetic energy can be represented by P square by twice m plus V. Okay, so you get E equals to P square by twice m plus V. As we know, again you just take start with that wave function psi. Okay, and you just take the first order derivative, second order derivative, space derivative, okay, with respect to position x, and you will get some value in terms of kinetic energy. And again when you try to take the derivative of that wave function psi in respect to time, so that time derivative will give you again some value in terms of energy. So now you just substitute all the value in the total energy equation, that is E equals to P square by twice m plus V. So substituting that value will give you the ultimate Schrodinger time dependent equation for a particle acted upon by a force field. Now I will show you step by step how you are going to derive this. So as I have told you that one-dimensional time-dependent Schrodinger equation for a particle acted upon by a force field. Let the particle of mass m move under the action of a force F function of x along the x direction. The potential energy V function of x is a function of x only and is independent of the time. So therefore the force field is a conservative one. Now if P be the momentum of the particle, then the total energy will be E equals to P square by twice m plus V, where V is the potential. So you know the total energy E equals to h cut omega. So h cut omega equals to h cut square k square by twice m plus V. I have substituted the value of momentum. Okay, so let the wave function represented by the particle is psi, function of position and time, equals to a e to the power I kx minus omega t. For the previous one I have also considered the similar wave function, so you just try to remember that wave function psi equals to a to the power I kx minus omega t. So you have to start with this equation. So first take the time derivative of this equation. So the first order derivative with respect to time will give you a within bracket minus I omega e to the power I kx minus omega t. So that can be written as minus I omega of psi. So or if you multiply both sides with I h cut, so you will get I h cut del psi del t equals to I h cut minus I omega into psi. So minus I into I, so it will be I square, which value is also minus 1, so minus sign will cancel out. So I h cut del psi del t, that value will be equals to h cut omega into psi. Now this is the first case. For the second one, again you have to take the position derivative with respect to space or position. So the first order derivative with respect to position x will give you a ik e to the power I kx minus omega t, and the second order derivative with respect to position will give you del 2 psi del x2 equals to minus k square psi. So that's equals to ik of psi. So multiply both sides of this equation, the second order space derivative, this equation, with minus h card square by twice m. So if we multiply both sides, I will get that h card square by twice m del 2 psi del x square equals to minus h card square by twice m minus k square psi. So minus minus will cancel out, and you will get h card square k square by twice m of psi. So if you take all this thing in the left hand side, so ultimately you can get that minus of h card square by twice m del 2 psi del x2 plus v of psi equals to h card square k square by twice m plus v of psi. So what I have done, I have added both sides the potential v. So here from the right hand side of this equation will give you minus h card square by twice m del 2 psi del x2 plus v of x of psi equals to h card omega. So that means h card square k square by twice m plus v, that's equals to h card omega. So now if we equating the left hand side of this equation 8.14 and 8.18, because these two equation right hand sides are equal, so from equating this left hand side, what I will get that I h card del psi del t equals to within bracket minus h card square by twice m del 2 psi del x square plus v whole into psi. So this equation represents a one-dimensional time-dependent Schrodinger equation for a free particle moving under a force field F. Now the next one, that is three-dimensional time-dependent Schrodinger equation for a free particle. Okay, so again the basic idea is always same. Okay, so first of all the students try to understand how I have construct the one-dimensional time-dependent Schrodinger equation. The basic process is also same for here, so only the difference is that in that case for one-dimensional you have considered only the direction, that means x or y or z, because you have considered only a single dimensional one-dimensional case. So here for three-dimensional case you have to take the consider it or into account that x, y and z three coordinate. Okay, so that means where as the previous procedure says that you have done the space derivative with respect to x only, so here you have to consider all the space derivatives. So here as you have tried to find out that del 2 psi del x2 value for the previous one, so here the second order derivative that you are going to find out of that given wave function psi with respect to x as well as y as well as z. So the combination of the three will give you the total solution or total second order space derivative of that wave function psi. So you have to consider for x, y and z. Now I will show you the procedure that help you to find out that three-dimensional time-dependent Schrodinger equation. So here the three-dimensional time-dependent Schrodinger equation for a free particle, for a particle moves in a three-dimensional whose wave equations can be represented as psi equals to a e to the power I k dot r minus omega t, where r equals to xi plus yj plus zk, which includes all the coordinates x, y, z. So where k dot r, that value equals to kx plus ky plus kz. So let us operate psi for a Laplacian operator grad square or del square. So del square value is the del 2 by del x2, del 2 by del y2, del 2 del z2. So then the equation 8.20, that means the wave function that I have considered here, you try to find out the first order and second order derivative with respect to x and y and z. So del psi del x will give you ik of psi, del 2 psi del x2 will give you minus k square psi. Similarly, you can write for the second order space derivative with respect to y will give you del 2 psi del y2 equals to k square psi, and the second order space derivative with respect to z will give you del 2 psi del z2 equals to minus of k square psi. So the grad square psi will give you the value. If you operate the Laplacian operator over psi, that will give you del 2 psi del x2 plus del 2 psi del y2 plus del 2 psi del z2. So ultimately you will get k square, kx square plus ky square plus kz square whole into psi. So that means minus of k square psi. Now if you multiply both sides by minus h square square by twice m will give you minus h square square by twice m grad square psi equals to minus h square square by twice m into minus k square of psi. So from the both side you can write minus h square square by twice m grad square psi equals to h square square k square by twice m into psi. So the above quantity will give you p square by twice m into psi. So again differentiating that wave equation with respect to time. So the first order time derivative will give you del psi del t equals to a of I omega e to the power I k dot r minus omega t. So from there you can write minus I omega of psi. So both side if you multiply by I h cut will give you I h cut del psi del t equals to I h cut of within bracket minus I omega into psi, that means h cut omega into psi. So as you know that h cut omega is equals to p square by twice m, and so I h cut del psi del t will give you p square by twice m into psi. So now you know that equation 8.23 and equation 8.22, the right hand sides are same. So similarly equating the left hand side will give you that I h cut del psi del t equals to minus h cut square by twice m grad square psi. So this equation represents the three-dimensional time dependent Schrodinger equation for a free particle. Next one. The three-dimensional time-dependent Schrodinger equation for a particle acted upon by a force field. Here also the procedure is same. You have to consider all the coordinates x, y, z. Okay, so here we considered a particle of mass m acted upon by a force field derived from a potential v. Let the wave function as psi equals to a e to the power I k dot r minus omega t. So as we have derived already that k dot r equals to kx, ky, k plus kz. Okay. So now the total energy of that particle is E equals to p square by twice m plus v. So now operating equation 8.20. So the grad square, that means Laplacian operator, as we know that value is del square equals to del 2 del x2 plus del 2 del y2 plus del 2 del z2. So again try to find out the second order space derivative with respect to x, y and z will give you del 2 psi del x2 equals to minus k square of psi, del 2 psi del y2 equals to minus k square psi, and del 2 psi del z2 equals to minus k square psi. So ultimately what you will get, adding these three, so that will give you the grad square. Grad square value is grad square psi. That value equals to, again you will get minus of k square psi, where k square represent kx square plus ky square plus kz square. Again you multiply both sides by minus h square by twice m will give you minus h square by twice m grad square psi equals to p square by twice m of psi. So adding both sides the potential value, that will give you minus h square by twice m grad square psi plus v of psi equals to p square by twice m psi plus v of psi. So that means in left hand side, if you operate the operator minus h square by twice m grad square plus v over psi, that will give you the value p square by twice m plus v that's over psi. So p square by twice m plus v, that's equals to h cut square k square by twice m plus v, that means equals to h cut omega. So ultimately you will get h cut omega into psi. Now again try to differentiating the wave equation that psi equals to a to the power I k dot r minus omega t with respect to time. So the first order time derivative will give you del psi del t equals to a within bracket minus I omega e to the power I k dot r minus omega t. So ultimately we will get that value equals to h cut omega into psi. I want to repeat because we have done this similar derivation previously. Okay, so now again equating the left hand side of equation 8.26 and 8.27, you get that I h cut del psi del t equals to minus h cut square by twice m grad square plus v into whole into psi. So these equations represent the three-dimensional time-dependent Schrodinger equation for a particle acted by upon by a force field derivable from the potential V. So if the particle is free, then V is equals to 0. So that will again reduce to the our previous derivation that I h cut del psi del t equals to minus h cut square by twice m into grad square psi. So these are your three-dimensional time-dependent Schrodinger equation for a particle acted upon by a force field. So these are the reference book. You may go through that book. You will find the basic concepts, lots of theory or problem numericals are given there. The evaluation process is same. You have to appear for a 70 marks end semester exam and internal exam for 30 marks. So hope all of you have enjoyed and understand today's class. So I have completed the derivation regarding the time dependent Schrodinger equation both for one-dimensional and three-dimensional case. In next year I will discuss the Schrodinger time independent equation for one-dimensional and three-dimensional case. So thank you.